CDAC plays a pivot.
This meeting is being recorded.
Nowadays, CDAC plays a pivotal role in advancing India's semiconductor vision through research and collaboration. The organization supports Make in India initiative by promoting an independent semiconductor ecosystem. So CDAC is now one of the key institution where we are enabling the other institute for doing project and support in developing different semiconductor products in our country. And CDAC is located in different locations. So we have centers in 12 locations across the country. Total around 17 centers. In Trivandrum, we have 2 centers. Similarly, in Bangalore also, we have multiple centers. So different centers are working in different domains. So the primary objective for forming CDAC is to work on this supercomputing or the high performance computing in late 1980s. And from that time onwards, CDAC is working on this high performance computing area. Now also we are executing a national supercomputing mission for developing indigenous supercomputers, and we have successfully installed many supercomputers across the country in different R&D and academic institutions. Another major area which now our focus is on the quantum computing. Similarly, we are working on AI and multilingual computing, strategic electronics, software technology, health informatics, and cyber security and cyber forensics is also an area which we are working for the past 3 decades. And education and training is another major area in some of the CDAC centers are working on. And I am from the hardware design group of CDAC Trivandrum. Our main focus area is the microprocessor design now, and we have expertise in ASIC design and FPGA implementation. Going forward, I will show you some of the products which we have developed and some of the ASICs which we have developed and proliferated across the country. And analog and mixed signal IC design. We have a strong capability, and we have another team working in the embedded system area, high performance PCB designs, and we have the precision assembly and testing facilities as well. So which we are using for many of the product prototyping stage. And today we are here to discuss more about our Digital India RISC-V program. This program initiated by the Ministry of Electronics and Information Technology, MIT. And MIT launched this program to develop indigenous microprocessors, and 2 of the institutions were identified. One is from the academia and another is from the R&D. And IIT Madras, they have developed a series of processors, as well as CDAC focused on developing a series of processors starting from microcontroller class to a high performance embedded class. So in CDAC objective, we want to create the microprocessors which can further go into industry grade silicon. And this program is also seek collaboration among academia, startup, and industries to build a strong, robust ecosystem in our country. And for developing the microprocessors, we identified RISC-V as an very suitable instruction set architecture, and which will allow us to design the processors in a very flexible manner. And we can also design processors starting from the microcontroller class to high performance embedded class using the RISC-V. And we have started this activity actually in 2010, nearly in 2010. The government is focused on developing indigenous microprocessors. So CDAC came forward with a proposal to develop our own microprocessors. So that time there was many questions. So why you are going for an indigenous microprocessor development? Many other processors are available. So even available in the country, most of them, all of them are developed by the other Western countries. And the another question is, if you are developing your own microprocessors, so which instruction set are you going to use? So there are open RISC, and Spark and different ARM and x86 different instruction set architecture was available at that time. So which one you are planning to use for your indigenous microprocessor development activities? So at that time, in 2010, 2011 time, so we are heard about this RISC-V initiative. So one of the professor, Kriste Asanovich, and few of his students from the California University of California, Berkeley, they have come up with a fifth generation of RISC architecture. So that's why it's known as RISC-V. And they have come up with an open source architecture. Everybody can take this architecture and develop their own processes. That means they can do their own implementation. So they can develop a processor with 3-stage pipeline, 4-stage pipeline, 6-stage pipeline, or whatever, caches, memory management unit, etc. And no need to pay any royalty to anybody. So that was the major advantage of RISC-V at that time. And when we chosen RISC-V in the initial stages, we are also not sure that whether RISC-V will be going to be a success or it will become a failure. So during that time, we had our team had a lot of discussions with Professor David Patterson, Kriste Asanovich, and they given a direction to take it forward with RISC-V, and we chosen RISC-V as our national instruction set architecture. And we have started designing processors based on RISC-V in early maybe in early 2015 2016 time. And this particular project was approved in late early 2018, so that we started these activities in much more wider way. And we have come out with a series of microprocessors now in our family. And going forward, I will be explaining about what are the series and how you can use these processes in your development activities. And for addressing the first question, so what is the significance of this indigenization? So if we have our own microprocessors, we can say that it is immune to sanctions. So now, because of different geopolitical situations, so many problems are there. So it is very difficult to get the advanced microprocessors or different chips. So if we have our own solutions, definitely it is immune to sanctions, and we can have secure products. So we know what is going inside, and we can ensure that there is no hardware trojans or nothing inside. And it's always will be cost competitive, because nowadays also, if you are using many of the electronic devices like mobile phones, laptop, smartwatches, etc., all of them are, or maybe 95% of them are powered by ARM processors, and indirectly you are paying a royalty to ARM. So it's a indirectly you are paying a royalty to ARM, because it is included as part of the cost, and you can't avoid that. So if you have a product, so indigenous product, no need to pay any royalty to anybody. And you can always say you have the self reliance in this technologies, and you can have products which can substitute the import products. And you can also ensure that it is free from all the encumbrances, so if you have an indigenous solution. And the advantage of using RISC-V is it is free from all the licensing fees. No need to pay any royalty. So if you are a part of a RISC-V foundation, so you can no need to be part of RISC-V foundation also. So you can access all the materials, all the instruction set architecture documents are available for free. You can develop your own processes. Can develop your own products based on RISC-V. No need to pay any royalty. And another advantage is it's an extensible instruction set architecture. RISC-V is an extensible instruction set architecture. So you can say that if you need a microcontroller class processors, you can go for a minimal instruction set architecture with RV32I or RV32E, and then you can have your own different variants. So if you want a processor to run Linux operating system, you can add few more extensions in addition to the base integer set. you can add atomic instruction set as well as multiply instruction set, so that it will be compatible for running in Linux operating system, or any operating system can run on a processor with minimal RB32 integer multiply and atomic instruction set. And similarly, you can have different processing modes also. You can have a machine mode or a supervisor mode or a normal user mode. So there are different privilege modes. Like in our computer also, we have an admin privilege and a user privilege or a guest privilege. Similarly, RISC-V is also providing similar privilege operating modes. So that will help you to design processes which are which having different capabilities. And when we are choosing RISC-V, so initially there was only around 30 members as part of RISC-V Foundation. Now, if you look at the RISC-V website, you can see that there are more than 4,000 members, and around 70 to 80 countries are working on RISC-V in different capacities. So these are the standard instruction set architecture. So to design a processor using RISC-V instruction set architecture, you need a minimum RB32 integer instruction set, or you need an RB32E integer set. So which is the difference between these two is in the E, we can use only up to 16 general purpose registers, but in the case of I, we can go up to 32 registers. And in the case of RV64I is also similar. So you can have few more instructions also will be added to the base integer set. And there are different extensions are there. So some of them are listed here, some of the standard extensions which most of the people are using. So if you have a processor, you can say that it is supporting RV32I or IMA, FD, B, C, etc. And if you need a vector operation, so you can have a V extension also. And there is DSP extensions, bit manipulation extensions. So you can add these extensions, depends on your processor performance requirement. So we are working on different extensions. Our processors are starting with bare minimum RV32I, and we have the processors which includes all these extensions also, RV32, IMA, FTC, B, and vector extensions. So as part of this program, CDAC developed a family of microprocessors. So it's not only a single processor, we have a family of microprocessors. So that's based on the requirements. So one processor will not suit for all the applications. For running small embedded IoT applications, you need a microprocessor with bare minimum instruction set support. And when you need a high-end, when you want to run a high-end Linux operating system and image processing applications, then you need a processor with 64-bit architectures, out-of-order execution, and the floating point and vector units, etc. So we have developed a series of processors which can cater to different requirements, and now it is available for academia. We are sharing processor IP for free. So any academia, they can come forward and take any of the processor variants. They can develop they can develop a product around it. So it's free for all the academic institutions now. And these are the different variants available now. The first one is a 32-bit single core, supports integer as well as multiply. So this processor can also be configured for RV32I or RV32E also, with 3-stage pipeline. The instructions follow the in-order instruction execution. Most of the people using this processor for small embedded applications, running bare metal programs, and somebody they want to run a Linux operating system on a 32-bit processor, they can choose this AT1051 variant, which is much more capable, adding more extensions. It supports integer, multiply, atomic, single precision floating point, and compressed instruction set. So compressed instruction set means the normal instruction sets are 32-bit wide, and if you have a compressed instruction set, instead of 32-bit, you can have a small instruction bit. It's a 16-bit instructions. It's implemented using a 5-stage in-order pipeline. And the third variant, we have the Vega AS1061. That's also supported different operating systems, the different RISC-V extensions. You can see that it's supporting the double precision floating point operations also. We have this variants which support bit manipulation operations, and it's implemented in a 6-stage pipeline and supports in order instruction execution. The last three variants are the high performance embedded variant. Uh, all are 64-bit, and it's also support multiple RISC-V extensions. And you can see that the major difference between the first three variants and last three variants are the last three variants are heavily pipelined. It's implementing a 16-stage out of order pipeline. So in the out of order, when you are designing a processor supporting the out of order execution, so you can really see the performance difference. So when you are having a processor with in order pipeline, when it hits on a load instruction or a store instruction which is got missed in the cache, the data, if it is missed in the cache, so that will there is lot of cycles it will take to get data from the next level of cache or from the DRAM. So in that scenario, the out of order processor perform well. So even if it's one of the instruction is waiting for a long latency data, so at the same time it can execute multiple other instructions, and the number of instruction executed per cycle will be much higher for this kind of out of order processors. And the dual core variant, we have already taped out in one of our SoCs, and that SoC is currently we have received the sample chips, and it is now in the testing phase. Similarly, the AS1061 is also taped out in an Indian SCL foundry. AT1031 is also silicon proven and tape out. We have development platform also based on AT1031. So most of the processors are either taped out in different SoCs, or all of them are proven on FPGA. So now it's available for the academia and startup, so they can develop different products around these processes, and which, as I mentioned earlier, so it's available for free for academia. So they can just give some request, or what is the kind of application they are targeting, and which is the processor variant they need. So they can straight away start using the processors for their applications, and we are providing all the necessary support. And this is the Vega SoC roadmap, and a few of the SoCs we are fabricating to demonstrate our processor capabilities. And the first three variants are already fabricated, and the first variant is commercially available, and the second and third variant chip, we have received the chip, and the testing is in progress. And currently our focus is on this Dhanush 64, which is a quad core based processor based SoC, and the currently the FPGA implementation and testing is in progress. So you can see that the pictures of the SoCs, all of them are completely indigenously designed, started from scratch maybe a couple of years back. And now we have this Tejas 32 chip, which you can purchase either from Amazon or from Robo or directly from CDAC. So these are the peripherals included in the Tejas 32, the processor ET1031 processor core, and multiple other peripheral controllers like UART, SPI, I2C, GPIO, PWM, timers, etc. And many of the products are designed around this Tejas 32. Different departments of CDAC, they have come up with different products which they have already using another microcontroller. They have replaced with our Tejas 32, and some of them are gone for the transfer of technology also. And many other private companies are also buying these chips and developing their own IoT boards and small embedded products. So which you can see that those are available in Probu and Amazon. So you can buy and use those boards also. And this Tejas 64 chip is fully indigenous. The fabrication is also done in SCL Chandigarh, and the you can see that the Vega AS 1061 processor is heart of this SoC with the DMA controller. It supports the display controller. Then the single stepping modules, debug modules are there, and memory controller is also integrated with, and gigabit ethernet controller is also there, so you can connect this kind of development board directly to LAN and uh, develop some products. And the low speed peripherals are also there, which is available in multiple numbers, multiple UARTs, UART SPI, so which is sufficient for some kind of embedded applications. And currently we are testing this Dhruv 64 chip is also available now, which fabricated in TSMC 28 nanometer Taiwan foundry. And it's a dual core processor. So you have two processors running at 1 gigahertz. It includes some additional logic, like when you have multiple processors, the major issue is the cache coherency. So how you are managing the coherency between the data moving across multiple processors. So multiple processors and processor caches. So there is a hardware mechanism developed by us. It's a cache coherent interconnect. So which will track all the data moving around the processors and do necessary action. And multiple levels of caches are also integrated. The level 2 caches and the high speed memory controllers are also integrated along with the chip. So DDR3 and 4 memories will be supported by this controller. You can see that in addition to the previous generation of chips, so there are lot more extra interfaces, like the static memory controllers, the multiple Ethernet ports, then eMMC and SD host, and different different peripheral controllers are there. So which are now currently we are testing this processes by booting Linux and running application. So hopefully we are also in the next few months we will also come up with some kind of a development platform where people can try their own applications. So this is a features of Tejas 32 SoC. All the details are available in our website, so you can always visit vegaprocessors.in, and you can go to the link products. You can see what are the SoCs and development platform which are currently available now. And these are the processor features. As I mentioned earlier, it's all the peripherals are there, and the frequency of operation is 100 megahertz, and it can target for a few applications, small IoT applications, remote sensors, system supervisors, smart meters, and smart meter also we have developed our own smart meters and some of the products. So this chip is available right now, and we have a few development platform also. Now many of the academic institutions, even the CUSAT also bought a few of the development boards, and similarly the other institutions, many IITs are also now they have purchased Aries V3 and Aries IoT platforms, and they are also training their students to use this development boards for different applications. And these are the development platforms. So if you see here, it's a small platform. You can plug in with the small daughter cards, or even small breadboard kind of applications. So you can use this as a compute engine. So many of the pins are coming out from this connector, so you can connect different modules and interfaces you can develop some of the products. So some of the products around this Aries Micro also, whoever visited the CDAC booth in any of the conferences, so we have demonstrated many different products around this Aries Micro. We have this IoT development platform also, which integrates the Bluetooth and Wi-Fi module, proximity sensors, accelerometer, gyroscope, humidity, pressure, gas sensors, buzzers, and push button LED switches, etc. So this can be very well suited for different IoT applications. And Aries B3 platform is looking similar to the Arduino Uno platform. So there are more pins are coming out from here. So all the Arduino programs can be run on this Aries V3 platform. And Aries Alpha platform is suited for people who need a small display or Ethernet interface or SD card interface. So they can choose this Aries Alpha platform. And Aries Dot platform for different wearable applications. And Aries Eco Development Board is also available now through Amazon and our website. So it's a bare minimum board, which is exactly similar to the Arduino Uno platform. All the pin numbers and programming interfaces are all similar. So you can just replace Arduino Uno with our Tejas 32 Eco Development platform. And Nova is another platform targeted for this IoT application, so which contains only this uh, crypto chip and Bluetooth Wi-Fi module and 3D accelerometer and gyroscope. And all these platforms are available for purchase through Amazon and Robo.in and Vega Processors.in development board also. So you can see all these platforms. And these are the other high-end SoCs, the Tejas 64, as I mentioned. So there are a lot of other controllers are also integrated with the processor. I don't know how many of you are familiar with this system on chip. So in the system on chip, we are integrating processors along with many of the other controllers. So when we are going for this integration, for their standard bus interconnect is also necessary. So in our all the SoCs, we are using this AMPA interconnect. Interconnect. So the advantage is it's a standard bus interconnect, and there are a lot of IPs are also available with AXI4. So our processor also we made compatible with the AXI4, so that if you have any third party interconnect, or if you are choosing interconnect from Xilinx Vivado, so directly you can connect it with our processor. And if you want to purchase any other IP from any other third parties, so suppose you need a USB controller or Ethernet controller or display controller from some other company, Cadence or vendor, so then also it will be compatible. That IP also will be compatible with the XA4 interface. So you can easily integrate all the IPs to the system, since we are following this standard bus interconnect. And these IPs are also available for the academy. Some of the IPs are free for academy also. Not only the processor, and some of the UART and other GPIOs and other IPs are also available, so that they can build their own SoCs for different applications. So maybe if you need a small SoC for smart farming or smart sensing applications, so if you buy a chip from outside, STM32 chip, there will be lot of IPs which are not required. So you may require only processor plus I2C or UART or SPI, small other controllers. But when you are buying some other third party controller, there will be lot of IPs which we are not required for our applications. So effectively what happens is, when you are taking a bigger processor, so it will the power consumption and the energy management, everything is a problem. So you can also have your own indigenous solution for different applications, and you can only integrate IPs which are essential for your applications. No need to take any off the shelf SOCs and develop the products. So that will be a game changer in the future also. So people now also many people approaching us they have some good plans to develop some indigenous product. Most of them are replacing the existing imported product, as well as they are also come up with many novel ideas. So like as I mentioned, so they are also planning to do many products for the different IoT applications and secure applications. And our Tejas 64 SoC, which we fabricated in SEL, which can boot Linux operating system. So here you can see that the development platform based on this Tejas 64. You can see that Ethernet port is there, USB ports are there, and display port is also there, and you have the SD card interface and memory interfaces. So all the interfaces are there, and we have demonstrated a single board computer application using this board. So you can connect a mouse, keyboard, and Ethernet interface directly to the board, and you can use it as a small computer running Linux operating system. And this is the SoC I talked about earlier. So this SoC is also fabricated. You can see that when we have the first SoC, it was very small SoC for some bare metal applications. So the next one was the Tejas 64, it's slightly higher applications for Linux based application. And the third one was much more complicated. So the complex SoC housing two processor IPs and all the other interconnect and interfaces. And this can be maybe one of the development board can replace some of these requirements for this Raspberry Pi development platform. Here also, all the processors, we are keeping the standard interconnects so that people can take this SoC reference design also, and they can add their own IPs and things like that. They can come up with much more better products. And from Vega processor family, so we have a series of processors, as well as we have the complete ecosystem also. So the ecosystem is also very important because once you take any of the processor or any of the IP from outside, so many of the processors and IPs are available in the open source domain. Even if you look at any RISC-V processor also, you can see different small RISC-V processors are available for free. So the complex IPs are not much available, but small RISC-V processors are available in different GitLab and GitHub links. So which many people are taking and using for some of the applications, but the hurdle there, the many people, they are facing hurdles in the lack of software ecosystems, as well as lack of integration guide and lack of integration support. And CDAC is focusing more on supporting the customers, as well as providing the software ecosystem. That's why we have worked on different IDEs, as well as different operating systems, which different customers can use for different applications. One of the popular IDE which we have modified is the Arduino IDE, where we have added support for our Tejas 32 chips. So now people who are using the Tejas 32, they can just install a package for the Arduino, and they can run all the existing applications in Arduino. They can run on this Tejas 32 platform also. And similarly, whoever using the Tejas 32 for industrial applications, so they are more familiarized with Eclipse-based IDE. So we have the Eclipse-based IDE also, which can be used for programming all the processor variants. We have ported multiple operating systems. Some of them are listed here: Linux, Zephyr, FreeRTOS, Fedora, Debian, and a few more are there. And that's also based on the customer requirements, and to prove our processes also, so that we can also say that it's well proven for multiple operating systems. And we are also providing Linux device drivers also. um, people who are using Linux or any operating systems along with some of our peripherals, so they need a Linux device drivers. So we have developed a um, device drivers for all the IPs and board support packages also. Now 100 plus libraries are available for the IoT applications. We have compiler tools, documentation, discussion forum, tutorial videos. Everything is available now. And these processors can be targeted for different embedded system, IoT, smart metering, and different applications also. These are the some of the products which people are developed around this
Average, sir.
using this Tejas 32. And here you can see that a CPU card for traffic control application. So here also the main controller is Tejas 32, and this is also now implemented in different cities. The trial is going on, and the AARL lab IASC, they have demonstrated a drone also using this Tejas 32. You can visit our YouTube channel. You can see that the demo of these drones also. And another one is the Quaril. They have developed a education kit based on Tejas 32. It's known as Advik kit. And smart energy meter is also developed by another our department. So the TOT also done for this smart meter. These are the some of the other products, ultrasonic liquid sensor and speed sensor, etc., are also developed using this Tejas 32. And now I will talk about a few aspects of this processor as well as the SOC verification. So when we are designing the processors, the major challenge is the processor verification. uh, when we are running different applications, you can see that the number of instruction combinations coming for different applications will be entirely different. So one person running some application, some image processing application, getting a sequence of instructions executed. For another person, the instruction sequence executed by the processor will be entirely different. So we can't vary all combination of instructions. And when we are trying to verify this processor using the simulation or that kind of mechanism, so this will be entirely very slow. So that's why we have a hardware emulator platform is also available in CDAC. So which is helping us to verify these processes in much more quicker fashion. So some of you are familiar with QuestaSim and the different simulators from Cadence or Mender, etc. Right? So when you are simulating, you can see that for running a 1 millisecond simulation itself, it is taking a lot of time, 5 minutes or 10 minutes, even an hour, depends on the complexity of our design. The Veloci emulator will help you in that scenario. Once you have a compiled design, you can run it very fast, and the visibility of signal is also similar to the simulation. Suppose we are planning to boot, or we are trying to boot Linux in simulation using QuestaSim as a simulator. It may take around 3 to 4 weeks, even 1 or 2 months also for simulating the entire design. So at the same time, if you port the design into this emulator platform, which is also based on different technologies, if you go to the different website, you can see that what is the architecture and how it works and all. So the emulator is a strong hardware platform. So the 1 month simulation or a 2 month simulation, you can complete within few hours in emulation. So it's a costly platform which is available and helping us to verify our processes in a much more faster way. And normally, how we can do verifications in emulation is the SOC is very complex, right? And suppose you want to verify this Ethernet communications. Suppose you have the entire SOC and you want to verify this Ethernet communication part. And there is a mechanism. So some virtual Ethernet platforms also will be available from our Ethernet IP, we can send some packets, and this the co-model host will emulate for that application which is running on the PC, will respond for this particular transfer, and you can verify that your IPs are functioning correctly or not. And when you are going for this SOC level verification, similar to the Ethernet, so you will have n number of IPs, right? So you can have a SPI, then you can have this quad SPI, I2C, PWM. So see, many IPs will be there. So there are different virtual lab platforms are available, which you can connect it directly with this Vega-based SOCs and write some applications on the processor will transfer some packets through Ethernet or through USB or the Ethernet SD host controller, and the virtual lab environment will respond to all the packets. So if the packets are transmitted correctly, so that you can verify your SOCs completely in the this kind of an emulation environment, so that you can ensure your first time success in the ASIC fabrication. Now I will show you how you can develop, since I told you that we are also now sharing the processor for academia, so that they can also build different SOCs around the Vega processors. And now we are providing Vega AT1051 based design. It's already available in the GitLab, so people are interested, they can go to the website, they can have access to this processor, and there is a video is also updated. So we have conducted some of the trainings using this processor, and based on the earlier feedback, so we have now updated our latest video, so that it is very easy for you to, I will play the video also after this few slides. I will play that video also. You can see how you can build a system on chip using the 32-bit Vega processor, and you can run some application even on the FPGA platform also. And this processor is very capable. You can run either the bare metal applications, or you can run Linux operating system, and above the Linux operating system you can run different applications. So it's a pretty complex design. And now we have in the website, in the GitLab, we have shared only the 32-bit variant. But suppose some of you need any other variants which I shown in my presentation, so we can give access to those processors also. Earlier, I have already explained what is an SOC, how the SOC look like. So when you have the processor, you are connecting processor to different controllers for building an SOC. And our processor supports this AXA interface. Since it's supporting the AXA interface, so we need an AXA interconnect in between the processor and all the other IPs. Okay. And now in the reference design, so we are using all the Xilinx IPs for creating the SOC. So we can have the processor with multiple AXA interfaces. You can choose a core crossbar which will connect this master to these slaves. The transactions will be going through this interconnect, and the response is also will be getting back to the processor through the interconnect. You can have the processor IP, you can have a crossbar IP, and you can select any of the peripheral IPs from the Xilinx IP portfolio. You can connect and build your own SOCs, port it to FPGA, and you can demonstrate different applications. So once you have this SOC on the FPGA, so you can have the application also, you can develop on PC, transfer to the board, and you can demonstrate some of the good application. And I will play one video so that you will also get some understanding about how you can build these SOCs. And maybe after this class, anybody is interested to use this processor for building your own SOCs, so you can also try this. Now here you can see that after selecting the particular FPGA, so you are adding the processor as an IP to the IP catalog. So then you can, this 8010 processor is available as part of this IP portfolio of this Xilinx for AMD Vivado. So then you can have this AXI crossbar with multiple ports, so that you can decide based on your application. So then you can just connect between the crossbar and the processor, so that it's ready. Then the clocking master is also required, so that you can generate the clocks. Now the clocks in the processor and in crossbar is there, and then you are adding different memories as well as the peripherals. So in order to run some applications, you need a RAM or a ROM, right? So we are adding these memories right now. So now the processor is connected with the memories, one of the memory. And now we have added one more memory. So one memory is the first one is using as the ROM, and the other one is using as the RAM. So now the processor, crossbar, and two memories are connected. Then we are going to connect another GPIO controller. Okay, so that you can control some of the some of the IOs using the processor itself. So so there is a bit mismatch between the GPIO in the IP catalog and the processor bus width. So you need a bus converter as well as a protocol converter also. Since the processor is supporting the entire AXI4, but the GPIO itself comes with an AXI Lite protocol. So you are using a protocol converter to convert from AXI to AXI Lite, and then some of these addresses are also giving in the AXI crossbar, so that the transactions will routed correctly to the peripherals based on the address. And then you can simulate the design. So I am slightly fast forwarding because of the interest of time. And once you have the complete implementation, so you can even download the bit file into a RTS7 board, and here you can see that the using the GPIOs, that LED is blinking. And if you need any other IPs, so now it's showing how you can add this UART IP, so that you can send some data to the PC from the board using the processor. So once you follow this steps exactly same, so you will be able to do the complete implementation on the FPGA itself. So now you can see that this character is coming, this data is printing coming from the FPGA board. So actually the processor is executing some instructions, and it's sending the data from the FPGA board to the PC. And now this particular application, GPIO application, is actually downloaded using this UART. So here in the next step, we are showing how you can compile your own application also. Suppose you have your own IPs, so then you can develop your own applications and port it on and run your own application also. So now, if you are interested to try out the Vega-based SoC design, So you can go to gitlab.com CDAC Vega. So if you have already access, you can see all the folders are available. So you can go to this SOC design using Vega 801051. If you go inside, you can see that the processor IP is there, and the whatever YouTube videos now we have played also there. You follow the step-by-step process so that you will also be able to build some applications using the Vega. And anyway, after this class also we'll be sharing this PPTs, so you can also use this links from the PPTs to access all the resources. And different applications are also developed using Vega series of processors. Different embedded and control applications are also developed. So now I will show you if you need any support, so you can access Google Groups. So groups.io, you can access, you can have any of your queries, you can post it to groups.io, and you can get all the information through our YouTube channels, all the tutorials, videos, etc. And now I will show you another video where some of the applications developed using the Vega processor.
इक्कीसवीं सदी हिंदुस्तान की इसका मार्ग एक ही है, आत्मनिर्भर भारत।
So I will play one more video. Yeah, that's all from my side. So if you have any queries, we can discuss. So otherwise, if you need any support, either you can contact this number, or even you can email to vega@cdac.in. Thank you.
Thank you, Libin, for that wonderful presentation. I am sure that um, most of our participants will be inspired to use the Vega platform, incorporate it in their projects. Any questions? So before anyone, I just have one question. That FPGA based, implementing on FPGA, is there any particular FPGA limitation like that, or even?
So right now, the entire video which we have posted based on an RT100T FPGA. So it's an RT A700T board from Digiland. So it's taken as the reference board. Otherwise, you can also use any FPGA board. Basically, we are providing the processor IP, so you can select any FPGA and you can do that. So our objective is also because when we are conducting many workshops. One of the workshops we are using the Tejas 32 chip and developing some applications, and another workshop we are conducting this SoC design. So since whenever you are following the instruction from the video tutorial, right, so you can build the SoC, but practically we are in the workshops we are explaining the end to end. So why we have chosen this controller and why you are selecting this particular option, and we are explaining end to end for the SoC design, and we are conducting the SoC design workshops. So students are very much interested in this kind of FPGA based SoC design, since most of them are not familiar with the SoC, so they are getting the entire design flow and the architecture, and they are able to demonstrate something on the FPGA after 1 or 2 days program. So they are very well happy. And my request is also the whoever in this faculties in this class, so they can also take this as an opportunity and train their students also with Vega. So it's not for proliferating Vega. That is one part. The other part is students also will get much more benefits than other application development workshops. So they are very well benefited by these programs. And we are also looking for candidates who are having knowledge in this kind of SoC design and FPGA implementation. So the industry academia gap also can be reduced using this kind of programs. So if you are interested to conduct such programs in your institute, you can also approach us. And based on our availability, we can't guarantee that all the programs will be conducted, but based on our availability as well as the other requirements, so we can conduct a few programs from our side. And we are also interested to train the faculties and students so that in the coming years they can be our extended arm for proliferating our indigenous technologies, so they can conduct much more programs than us and promote Vega as well as this indigenous technologies among students. So this will be students also will get much more benefited. Yeah.
Yeah, there is one question from Mr. Danish in the chat window. What is the difference between emulation and simulation? Are you emulating Vega SoC in that setup?
Yeah, definitely. So as I mentioned in my talk, so when you are doing a simulation, you are doing it on a PC or a workstation, right? You are using the Questa sim or any other sim in the Cadence simulator. So the problem is when you are simulating a big design. So if you are simulating a counter or a small design, so that you can't see any difference. But when you are simulating a processor like this out of order processor and multi-core processor, so we want to verify the processor, right? So we want to ensure that processor will be able to boot Linux. How can we verify that the processor will boot Linux? So we need to simulate some Linux binaries and see whether processor is able to boot Linux. So when we are doing that process in simulation in normal PC may crash multiple times, and even in a normal PC it will take 1 month or 2 months to get the complete simulation over. So instead of that, there is a platform called emulator, so which is provided by this vendor and Siemens and many other people, only few people. So similar to the FPGA, we need to have some tools to put our design on emulator. So the advantage is we can see all the signals. So in the simulation, we can watch all the signals, right? But when you are going for an FPGA, we can't see any signals. So you can see few signals using ILA and all, but you can't view all the signals. But in the emulator, it is faster than simulation, but slower than FPGA. But the main advantage is you can see all the simulation signals. You can match all the signals, and simulation is very very fast. So you can do a Linux boot in few hours basically. So that's the advantage.
Yeah, hope that answers the question. Any other queries? I think that's all the questions. So
Yeah,
yeah,
you
once
can,
again,
no issues here. You can reach out to us anytime. So our contact details, phone numbers, everything is available. So you can reach out to us anytime for any queries and any support. So once again, thank you, Nalesh and Kusa team, Tripti and all the other team for giving us this opportunity. Looking
yeah.
forward for more collaboration and active participation in other activities also.
Yeah, thank you, Libin. It has been an honor for us to have you here as part of this program, and thanking you once again for accepting this invitation. As mentioned, I think we will share the material also with the participants. With that, we can conclude this meeting, this session. Yeah, thank you, Libin.
Yeah, thank you. Thank you once again. Thank you. Bye.
Bye. To the participants, we will start the next session at 7:30. Sorry that I have to end the meeting now and restart it at 7:30. This is for my otherwise taking attendance with a continuous session is difficult. So I'll hope uh, that's okay. So I'll end the meeting now and then we will start exactly at 7:30. Thank you.